Now, remember we said that positive work becomes kinetic energy, right? Now, a lot of people are saying, it's asking, what is the kinetic energy of the sled after 5 meters? And a lot of people are saying, there's the equation for kinetic energy. Let me get V and I can figure that out. But that's not what we want you to do, right? Because we don't know V. But what we do know is that work, positive work, becomes kinetic energy. So from what's given, the problem, we could figure out the work. So the net work. So let's figure out what is the work done by each force. So first by the 100 Newton force. So that would be W equals FD cosine theta. Now, to get that, you would put in the force is 100 acting on the sled, and it's pulling through a distance of 5 meters, and the cosine between, let me just draw this here. Here's the sled. The angle is like this here, 30. Okay, so the angle between them is 30, cosine 30. Want, and that gets you 433 joules. Okay, so that is the work that the pulling force does. Now, some of you guys, what you did was you went ahead and found the components, right? Some people saw this was 86.6 and this was 50. So then what some people are doing is, well, I'll get to it. So this is what they did. Okay, I'll come back to that. Now we want to calculate the work done by friction. Okay, again, it's W equals FD cosine theta. Friction is still going to be applied through 5 meters. Now the cosine for friction is going to be 180, right? It's always opposite the displacement. So 180. The question is, what is the friction force? So we know that if I draw the free body diagram here for this guy, we would have the mass was 10, so this is 98 is the weight. The y component is 50, and that means the normal force is 48. And if the normal force is 48 and we calculate friction, we have 0.20 times 48, or 9.6. So there's actually a friction force here of 9.6 newtons. So that is what force goes here, 9.6. And that is negative 48 joules. So while you're doing positive work, friction is doing negative work. Okay. Now, just to show you what I was going to say here was what some people did was they said, well, 86.6 is the x component. And so when they went to calculate this work here, the work done by the 100 Newton force, they did W equals FD cosine theta, and they put 86.6 times 5 times cosine 30. And you see why that's not right. Because 86.6 is 100 times cosine 30. So you don't want to figure out your component there and then use cosine 30 again. So if you choose to use 86.6, you can't use that, because then you're not going to get the right number there. Okay? So I just wanted to point that out. So that's why the equation is what it is, because the angle gives you the correct component automatically. Right? So this is how really you should do it. Other people found the net force and then did the work, and that's okay too. But it just gives you a little bit more work down the line for some of these questions we ask. Now, we have both works that were done. Now, to find the kinetic energy, we know the net work becomes the kinetic energy if it's positive net work. So the net work is 433 plus the negative 48. So that's 385 joules of net work. Right? And our equation tells us that net work equals change in kinetic energy. So let's just look at the work energy theorem. The net work was 385. The final kinetic energy, 1/2 mvf squared is what we're after. What was the initial kinetic energy? 0, right? So that means that the final kinetic energy, 1/2 mvf squared, is equal to 385 joules, and that was your answer to number 1. So the network is the final kinetic energy, and that's because the kinetic energy initially was 0. Now number 2 said, how much work does, what? Oh, how much work does friction do over the 5 meters? Now there's no, you don't have to do any calculations because you already did it. How much? Negative 48 joules. Number 3. What is the speed of the sled at 5 meters? Well, we know at 5 meters it has this much energy. Right? That's what we found. And we know that energy is 1/2 mvf squared. So all we're going to do is take 385 equals 1/2. The mass is 10 v squared. So v is 8.8 meters per second. Number 4, how much work does the pulling force do through 5 meters? How much? 433. Number 5, what is the kinetic energy before it starts being pulled? 0, right? Because it was at rest. So hopefully we're beginning to see that not a lot of work is required after this. How much net work was done on the sled to the 5 meter mark? 385. Number 7. If the rope is released at 5 meters, how much work will be done by friction to bring it to rest? Negative 385, right? We need to, it has 385, we need to take it away. So we need to do negative 385 joules of work. Number 8, what will the kinetic energy of the sled be once it comes to rest? 0. Good. Number 9, how much energy is lost from the time the rope is released to the time it comes to rest? 385 joules. Okay, and the last question, number 10, you got to do a little thinking now, little work. How far will the sled slide after it's released? So, work is FD cosine theta, that's where we get our distance from. We said friction is going to do negative 385 joules, so the work is negative 385. The force, we're going to find. The distance is what we want to know, and because we're dealing with friction, it's cosine 180. Now, once I release the rope, what happens to my free body diagram? Huh? Right, this goes away because there's no more tension on the rope, and my normal force goes up to 98. Right, 98. And that means my friction force is going to be different than it was when I was pulling. So this is 98, and this becomes 19.6. So then 19.6 is the actual friction force, and now you solve for D, and you see that the sled goes 19.6 meters. Your negatives cancel since you have a negative 1 here. And that's how far it goes. So let's see, we started that at 17 and it took 9 minutes.